Hey, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, the G-PST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scale and scope. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support, and open data and tools. More information on the G-PST can be found at globalpst.org. ESIG serves as the lead on Pillar 1, and as such would like to welcome you to our monthly joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and academia participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we're going to be using the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG10 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar is on the topic of weak grid interconnection of inverter-based resources, or IBR. Based on the number of registrations, this is shaping up to be another all-time bestseller. The increased interest around the world in applications of power electronic resources interfaced to the grid, like wind, solar, and batteries, is intense. Today's webinar will feature Sebastian Achilles, Managing Director for Power Systems Operation and Planning at GE Energy Consulting. Sebastian has 25 years of energy industry consulting experience on a broad range of power system engineering, planning, and operating issues, with 20 years of that at GE. He's a former chair of the ESIG Reliability Working Group, which has been deeply involved in the issues associated with high penetrations of IBR, weak grids, and grid-forming inverters for the last few years. His team provides support to GE product design related to grid behavior of IBRs. The team also provides consulting support to developers and transmission entities related to the same area of expertise. Sebastian's a good friend and a good friend of ESIG, and I feel very fortunate to have him here with us today. The webinar today will focus on the interconnection of IBRs viewed through the lens of weak grids. As a note of interest, Sebastian gave a similar webinar in the ESIG webinar series about 4 years ago, thus the byline of "Why are we still talking about this?" In the meantime, nothing has changed and everything has changed. Sebastian will update us on the implications of massive deployments of IBR with observations based on recent experience, of which he has a lot, as you will shortly see. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG10 to ask your questions. And without any further ado, let's go ahead and get started. Sebastian, I'll now turn it over to you. Sebastian, I think you're still on mute. I don't hear you.
Can you hear me now?
Yes, now I can hear you. Okay,
sorry about that. Thank you, Charlie. Thanks for the introduction and thanks for the invitation to share our experience on this topic. Thanks for the opportunity to be part of this seminar assignment. I definitely will be relying on many of the previous seminars, some of the stuff I'll be describing, and I look forward to the question and answer sections. Thanks everybody who is joining the session. One comment about my background, the background of the team I work with. We are part of a vendor of equipment, GE. We participate in projects related to onshore wind, offshore wind, solar, batteries, in some aspects of facts. So the experience that I'm going to be describing this from the point of view, to some extent, of an OEM, but also to some extent as a consultant, and the experience of helping develop products that meet requirements and can connect in weak grid conditions, and also from the experience of supporting developers and transmission companies in evaluating those projects. So I'll get to it. The why are we still talking about this? Like Charlie mentioned, is not in the context that this is not important. We do think that this is an important subject, but it is true that we've been talking about this for a while. There are some aspects that have not changed, and there are some aspects that are changing rapidly in recent years. So definitely the intention is to particularly elaborate on the new subjects. This is a brief outline. So the first bullet is related to the things that we've been talking about for some time. So what are the performance challenges related to weak grid connection of inverter-based resources? What are the mitigations? And a little bit on what is the project experience. Here, project means connecting a wind plant or connecting a solar plant to a particular grid, and from the OEM side, supporting that connection process. So what are the things that we see repeating in many of those processes? After that sort of introduction of subjects that are probably not going to be new to many of you, the idea is to talk a little bit about what we see changing. And maybe those subjects are also not new to you, but you would probably agree in that case that there are some aspects of weak grids that are being different. And those are the aspects that we would like to elaborate further. After that, we felt that it was good to talk a little bit about grid following and grid forming. There were some seminars in the past in here, and a lot of work in the industry about this different ways of controlling inverter-based resources. So the idea is to refer to those two type of inverter or control technology in the context of weak grids. Then a few comments about your SQL ratios and screen aspects that we see changing, and a few final remarks. So to get started, you can see in the title we said nothing new. Sorry about that, but I think we need to start from the stuff that we've been discussing for a while. So as you can see in the upper left, you see a picture of a wind plant. In this case, it could be a solar plant or battery that connects through a long transmission line to a bulk power system. So in general, weak grid very often in the industry is referred to as a system like this, where you are connecting an inverter-based resource plant at the end of a long transmission line. The nomenclature weak grid or low system strength refers in general to the fact that the voltage at the point of interconnection, or in general in the bulk power system, is significantly affected by the currents injected by the inverter-based resources. So if you look at it in the opposite way, if this wind plant will be relatively small, whatever current it injects, it won't really move the voltage too much. So that will be a strong connection. A weak connection will be the opposite of that. There are other aspects of weak grid that I will mention later in the presentation that are mostly related to, they're more related to the angle of the voltage instead of the magnitude of the voltage, or the frequency in the system. So initially, I think in line with the way the industry mostly talk about weak grid, I was referring to the impact on the voltage magnitude of the injection of current from inverter-based resources. So in this regard, the main challenges are typically related to fault behavior. So there are faults in the power system, having this plant surviving or tolerating the fault and recovering during an N-1 or even weaker conditions. There are demands of making sure that the system and the plant together can survive low voltage right through and high voltage right through conditions, and the potential angle shifts that could occur. This is not a new problem. There has been significant improvement in technology of inverter-based resources and in understanding of the problems as well, that has allowed many of these plants to be connected in conditions where very close to the steady state operating limit. So now referring to this graph here in the lower left, this will be the voltage at the POI, and this is the power generated. This is a typical PV curve. The red curve will be the performance of the system, and basically there is a steady state limit in which we cannot push more power in the system from this plant beyond what is tolerated or demonstrated in the red curve. So the technology of inverter-based resources has progressed during the years such that we're able to get really very close to the nodes of these curves for the weakest conditions of the system. And that's, I'm not necessarily speaking for the particular company I work for. I think in general, the industry has been able to do that with the different inverter-based resources that are deployed. There are many utilities, transmission companies, system operators that have processes on how to evaluate or what studies to do when the system is weak. I wouldn't say that there is a consensus on how to do this, but there are many companies that have their process around this. Very often, electromagnetic transient studies are required to study this in detail, and many of the learnings of this have been incorporated in manufacturers' design processes. So a couple of examples. So what can go wrong if the grid is weak and you have inverter-based resources? Well, again, this is nothing new. Here we characterize two types of stability issues as fast control interaction challenges and voltage collapse challenges. So concentrating on the problem on the left, there are 3 inverter-based resource plants that are connected through a long transmission line, through a substation that has an SVC, and then through a couple of long lines to the rest of the network. There is a particular contingency that consists in losing one of these lines that results in the system being extremely weak. Now, I'm saying the system getting extremely weak means that the injection of current from these inverter-based resources has a significant effect on the voltages of the network. Let's say if in this case you have 2 wind plants, wind plant 1 and 2, and you add wind plant 3, the extreme weak conditions is for everybody, not only for the last plant that you connect. So this particular condition is characterized then for this inverter-based resources, the cluster, some of the 3 seeing an extremely weak condition. When this fault is applied and clear, so after the clearing, this plot here on the left shows the behavior of active and reactive power as seen from the wind turbines. And in principle, what you can see here is that the reactive power has an oscillation between 5 and 20 hertz interaction. And if you would, so after assessing this, it was clear that the SVC was participating in the interaction. So in this case, there was a clear interaction between power electronic control devices that basically would cause the system not to be able to recover. Interestingly, if you would subject, if you would take this inverter-based resources and have them survive a similar voltage or similar fault condition with a stronger grid, they will survive. If you would do that with the SVC, they will survive. This SVC will survive, but when you put them together and the system is weak, they start interacting. This particular problem was solved actually by modifying the inverter-based resource settings, the voltage regulation. The SVC modification was also an option that was feasible at the time. This plant has been operating for many years. The problem on the right, I'm sorry, and then this is called fast control interaction because you have two power electronic control sources or devices interacting. Voltage collapse in an inverter-based resources. So in this case, again, many plants or a cluster of plants pushing power through a long line, you have a remote fault, and there is a problem. So this here are field recordings. You can see the upper plots are voltages. The pink is the sending end, and the darker line is the receiving end voltage. And then the lower plot are active power, again, receiving end and sending end. What you can see, there is between the green lines, there is a fault. As a consequence of the fault, the wind turbines reduce the active power to reduce the risk of collapsing voltage during the fault and having trips during the fault. At the time of clearing, because the active power from the turbines is lower, the voltage in the system gets significantly high, right? So you have a weak system with significant capacitance. If you reduce the amount of power you're pushing, the reactive power consumption in the system is lower, and for that reason, when you clear the fault, you're pushing less power, the voltage gets really high. Nothing new there, perfectly stable, no problem with that. Now, after the initial transient, the active power starts increasing. And when the active power starts increasing, the voltage starts collapsing, and this basically ends up collapsing. There was a voltage collapse in this case. The voltage collapse is relatively fast. It was like a 200, 300 millisecond phenomena, and that's fast. The voltage collapse is as fast as the active power recovery, in this case from the inverter-based resources. This problem was resolved also by modifying the reactive power controlling inverter-based resources to make sure there was enough reactive current in the system to sustain the power transfer when the power was increased. This plant has also been operating for many years stably. So these are two examples of the type of issues that you can see with weak grids. So what are the mitigations? So from the OEM-oriented description of the mitigations, so in some cases you may need to do some mitigations. In some cases, even with low system strength or weak grid conditions, you may find that the system is stable without having to do anything beyond the standard approach. Now, mitigations could include aspects related to making the system stronger, like transmission upgrades with additional lines, avoiding having radial operation and more meshed operations so that the impact of tripping a line is smaller, adding series compensation. Synchronous condensers can improve the system strength. SVC and STATCOMs are a dynamic source of ours, so they could help. They have control challenges, as we saw before. There could be some interactions, but as long as you take care of the interactions, this could be a mitigation. And then in some cases, you could have special protection schemes where you reduce the amount of power injected into the system in extreme conditions to avoid unintended trips. And the other option, of course, as I mentioned before, is to modify controls or tuning in the inverter-based resources, and in some cases in the plant level controls. Now, from the OEM perspective, typically an important point is, well, we have to be careful not to give the impression that whatever problem there is, it can be fixed with control tuning. That's not always the case, but definitely many things can be done there. So this is the old stuff. What do we see in projects, right? So we have projects when they get connected, and there are potentially, it's identified that there are weak grid conditions. What do we see there? So very often, developers will obviously prefer to explore control modifications in the inverter-based resources before anything else because of the cost implications of the other aspects in the list I mentioned. Potential issues that we see, so the problems, as I mentioned before, are typically related to fault behavior. So if we were to look at small signal and large signal perturbations, the small signal perturbations with weak grid are typically resolved in the industry by now. So most inverter-based resources are small signal stable, even in very weak grid conditions. The challenges are more related to fault, surviving fault, and the recovery after the fault. Another issue that is not too uncommon is when there are requirements of having maximum and fastest possible response time. So very aggressive controls or very fast control requirements in weak grids, those two don't go together. So very often, after a long process of studies, there is a conclusion that some of the controls need to be slower for weak grids, despite the fact that maybe the requirements ask for very fast response in a standard application. In more concrete details, some of the modifications that are typically performed are the slowing down the active power recovery is a very common aspect that is observed, necessary. This is not so much related to the inverter-based resource not being able to inject power quickly. It's kind of a combined aspect. So it's also related to the system being able to take a lot of power very quickly when there is a big electrical distance between the point of interconnection and the rest of the network. High voltage magnitude control is important, as we saw in the previous plots. When you clear a fault in a weak grid system, you tend to have high voltage. Absorbing reactive power to avoid the high voltage, but not absorbing too much to create a voltage collapse is a non-unusual subject. Control adjustments of the new plants versus the old plants that are already there is also becoming more and more common. I'll talk a little bit more about this, but you connect a new project next to an old project, and then when you make the grid weak for everybody, including the old project, having to do control adjustments, considering the fact that you have that older equipment there is actually relatively common these days. Slowing down SVCs and STATCOMs, so there is a practice in industry to make SVC and STATCOMs as fast as possible for the conditions when you commission the SVCs. A few years later, you connect a lot of inverter-based resources around it, the system gets weaker, and these devices go from very fast to a little bit unstable. So that's not unusual. And yeah, I'll stop there. So moving on. So what do OEMs do about weak grid? So in principle, when you look at the different controllers in a plant, so if you have a solar plant, you will tend to have a microprocessor that controls the power electronics. You wouldn't have turbine control. In the case of the wind turbines, you will have a turbine control and a converter control at each turbine. And then independently of the type of IBR, you will normally have a plant controller. Most of the weak grid aspects are related to a fast interaction with the grid and affect mostly the converter control. And the aspects that have to be tweaked are usually related to sensing where the condition in the grid and adapting the response of the IBR to that. So having prescriptive responses like injecting reactive power no matter what, or absorbing reactive power no matter what, those are the type of things that are not good for weak grids. So typically getting excuse me, an inverter-based resource to behave better in weak grids is related to improving how the inverter-based resource adapts to what's going on in the grid. So manufacturers typically have processes around products more than projects. So let's say there is a new wind turbine product, there is a process to design that product. As part of that wind turbine, there is an aspect related to the converter control. Those products have relatively short cycles, so you can familiar with the fact that wind turbines or solar inverters or battery inverters don't last in the market for too long. They're like 2-3 years later, you will find an upgrade of that product being offered to stay competitive. So that's a characteristic that challenges a little bit OEMs. The way this is affecting, the weak grids are affecting these processes is that OEMs tend to include a large range of system conditions, including weak grids. And the idea is to simulate those or to test those in a lab and container to make sure that the converter controls and the converter in general can react, does not trip, does not get damaged, and it has the type of injections in the system that are compliant with most of the applications. But an important point is that at the time of designing that product, you don't really know the specifics of any particular project. It's a product what is being designed, not a project. And in general, over the last years, there has been way more sophisticated performance evaluations in this product performance to try to anticipate issues. And then at the time of the project, basically, I think all OEMs are getting better at creating simulation models that reflect the details of the products, supporting interconnection processes, and interpreting the different interactions that happen. So I think overall, the industry is getting better at this. So weak grid connection of IBR, what changed, right? So the slides that I got up to this point were kind of old slides. I've used them before. You've seen slides like that or better in the last year. So what is different? So some of the things that are changed, if you look at the subject of the left, is power transfer challenges. This is pretty much the same problem I mentioned before, where you have a plant and you're trying to push power through a long transmission line. So this is still there. What happens now more and more often is that you are doing this in a location where there are other plants there. And when you connect a new plant, you make the system weaker for everybody. So interactions with this older equipment, in addition to keeping the system stable, is relatively common these days. And we continue to see the subject of connecting particularly large projects through long transmission lines. That is still there. Particularly, I think in North America, there's a trend right now which are relatively large projects getting connected. Now, the other type of problems that we start seeing is, I'm calling them here, high inverter-based resource penetration challenges. So differentiating from the one on the left, in this case, you have a new plant, but you're connecting it close to solar, batteries, not too much synchronous machines, loads, and all of this system is weakly connected to the rest of the system. So this scenario is not too frequent at this point, but it's becoming more frequency, and it's definitely in the minds of those that are making sure that the grids are reliable throughout the lifetime of the wind plant, right? So if you connect a wind plant or a solar plant today, it's going to stay there for 20 years or more. So transmission companies or system operators are envisioning scenarios where this will be common. And this is now part of the challenges that needs to be addressed in the interconnection processes. I'm purposely defining this problem as not related to a power transfer problem. You could have both problems, but in principle, although you have a weak connection, you're not pushing a lot of power through it. In this case, you have other problems more related to the inner loops of the controls, the converter controls in the different equipment. The old or the new one make it unstable because the system is actually very weak. There are more aspects related to the frequency may have changes that are really fast because you don't have significant synchronous machines, or angle fluctuations in some of the buses in this area could be very significant and cause trips. In addition to that, system restoration could be an issue. So in general, we see that the increase in inverter-based resource penetration that exists prior to connecting a new project is sort of shifting the focus of weak grid connection from what I mentioned in previous slides to what I described here. So now let's elaborate a little bit more on this. I'm going to try to talk a little bit about the implication of this and how this is changing the way we talk about weak grid. So I'm keeping here this power transfer challenge picture that we had before, and this is intended for the other problem. So if we try to do a very simple system that sort of reflects this, at least conceptually, we can come up with something like this. We'll have the inverter-based resource connected through a large reactance. to a source. So this will be the Thevenin equivalent. In this case, the equivalent I'm proposing is kind of the same, but it has a load. And this load has the effect that the generation of the inverter-based resource is partially consuming the load and is partially transferred through this reactance. In the case in the left, all the power generated by the inverter-based resource is transferred through the reactance. So now, speaking of short circuit ratio and how it affects this problem, or what it means for these problems, in principle, the short circuit ratio, as it's usually defined, it will be the ratio of the short circuit level at the terminals of the inverter-based resource divided by the megawatts, the rated megawatts of the inverter-based resource. If we, for example, say that the short circuit ratio is 0.5, I know this number sounds crazy because we typically talk about numbers higher than 1. If the short circuit ratio is 0.5 means that this reactance will be 2 per unit in the base of the inverter-based resource. So let's assume that. Let's say, well, the short circuit ratio is 0.5. This reactance is this big. The system in the left is basically completely unfeasible. It's just not possible in steady state to push 1 per unit power through a system with this short circuit ratio if the voltages are reasonable. The system on the right, on the contrary, does have a possible steady state operation. So you could have this system being stable in steady state with a short circuit ratio of 0.5. So what this means is that depending on what kind of scenarios we're looking at, the short circuit ratio of 0.5 could mean a clearly unstable, impossible, not feasible condition, or a potentially feasible condition. So the same SCR means something different in these two systems. Further elaborating on that, if we now look at a number of operating conditions, so this little figure here on the right is what it defines the different columns here in this table. So if this load, for example, is 0, then this system looks like the system of the power transfer challenge. If this load is different from 0, we start looking more like this. Now, I'm going to refer now to grid following and grid forming. That are some of the concepts that were discussed in some of the previous webinars. In general, grid following is the type of technology that has been deployed in grids so far associated to inverter-based resources, and grid forming is seen as the new type of control approach that can solve some aspects of high penetration of inverter-based resources. So here I would like to look at that, look at the differences between the two in the context of weak grid systems. So if we concentrate on the first 3 columns, which is what we are accustomed to talk about in the industry, this load is 0 megawatts, meaning that we're basically looking at this power transfer challenge aspect. If the short circuit ratio is more than 1.5, we could argue, depending on the technology, maybe a 2.5, but there is a value that higher than that, grid following or grid forming technology are perfectly stable. There is a steady state point of operation that works, and there are many applications working in this way. If the short circuit ratio is between 1 and 1.5, this will be a really weak condition. Well, kind of depends on the controls and some of the characteristics of the grid. Potentially, this could be made to work with both grid following and grid forming. Below short circuit ratio 1, it is not possible to have a steady state operation of a system like this. So it doesn't matter if you have grid following or grid forming, this type of conditions are unstable. So grid forming, short circuit ratio slightly less than 1, it will be unstable, grid following the same. Now, if we start now looking at scenarios where the load is different from 0, we're actually not transferring all the power through this reactance, we will find that with a load of 0.5 per unit, short circuit ratios well below 1 are stable even with grid following and grid forming. As we continue to reduce the short circuit ratio, we will find some conditions where this may or may not work. And then if we push the short circuit ratio such that the steady state condition is not feasible, both of the concepts, grid following and grid forming, are unstable. And then this last one here is the main reason for grid, one of the main reasons for grid forming being discussed is if you have a short circuit ratio that's really, really low, and you have a significant load, so power transfer is not an issue, grid forming will be stable and grid following won't be stable. So one of the points I'm trying to make here is that if we're looking at this type of challenges of weak grid power transfer challenges, both grid following and grid forming have a similar behavior. There shouldn't be significant expectations that grid forming is going to solve this type of problems. Now, in scenarios where you have an area where very low or no synchronous machines, grid forming will tend to be stable and grid following will not, or not necessarily. So that's one point I wanted to make. So grid forming has important advantages, but not necessarily related to power transfer constraints, which is the most typical way the industry refers to weak grid systems. I don't mean to attack grid forming. It's a great technology, and there are important advantages of grid forming related to the response to voltage angle jumps and fast rate of change of frequency and potentially system restoration and black start. I'm not going to elaborate on this. This was elaborated in previous webinars, but I just want to make the point that grid forming is a great technology, just that the advantages are not necessarily related to the power transfer challenges I was describing before. So a few more points, last two slides. SCR metrics. So short circuit ratio type calculations are very simple calculations, are typically used in the industry to sort of assess initially, do I have a weak grid or is it a strong grid? Do I need to be concerned about this? This has been used in the industry for a long time. So a couple of points about how the industry is operating in general. Most likely all of you know this. The calculation of short circuit ratio without consideration of multiple inverter-based resources is highly optimistic and not recommended. So if you have an area that has many inverter-based resources planned close to each other, and you do the short circuit ratio calculation of one plant, ignoring the others, you're going to get very optimistic results. That's highly discouraged, has been discouraged for a long time. Nothing new there. SCR metrics that consider the multi-in-feed are recommended. Weighted short circuit ratio, composition circuit ratio, there are others. Here I mentioned a NERC reliability guideline. There is also a SIGRE before 62 publication. There are several other before publications related to short circuit ratios that consider in feed. Those are the ones that are recommended, and you will basically calculate short circuit ratios that represent how weak an area is, not how weak a single project is. And then there are a number of steps that are done. So if a transmission company of reliability entity calculates a short circuit ratio at the point of interconnection or a high level, there's sort of a translation of that short circuit ratio to the terminals of an inverter-based resource, and then the manufacturer of the inverter-based resource may provide guidance on to what extent that level of short circuit ratio was incorporated to the design, if there are risks or not. And based on that, there could be decisions about doing detailed studies. Now, the aspect that is new, or that, I'm sorry, it's new to me maybe, or to us, is that we're seeing many scenarios that are more related to the high inverter-based resource penetration. Like in the previous slides, the stuff on the right, where the power transfer is not really the challenge. It's more the fact the system is weak because you have very little synchronous machines close by, but you're not transferring a lot of power through the weak connections to the grid. In those cases, the short circuit ratio calculations, the ones that are typically recommended, including the multi-in-feed, tend to be quite pessimistic. So we're finding many cases where we estimate the short circuit ratios that are below 1, that will be typically very concerning. But actually the plans work. The detailed studies are performed and the plans are commissioned, and there is actually no issues. So that is what is new. Still, I don't think there is a clear metric to be able to say, well, we should dismiss what we were doing before because that's too pessimistic. I think there is an exercise of finding something that is maybe not as pessimistic but reliable to avoid doing studies when there are actually no significant risks. This is some of the things that are new in that front, at least from where I'm operating. Last slide. Just as a summary, the power transfer constraint project. So when weak grid is associated with pushing power through a long transmission line or through a large electrical distance, That is challenging, continues to be challenged. That is not to the industry. There are ways of analyzing this. There is not necessarily agreement and consensus in the industry how to do it, but there are several system operators that have found ways of doing this in collaboration with developers and manufacturers. Manufacturers have accommodated their processes to incorporate some of these scenarios in their design processes to improve the performance of the inverter-based resources without having to adapt many things for the particular project. With this, I don't mean to say that everything is resolved, but there's quite a bit of work that was done there. New challenges seem to be more and more frequent in projects or discussed more frequently in the context of either current operation or expected operation of a plant when it's commissioned, or maybe many years during its lifetime, looking at scenarios where power transfer is not the issue, but the system is really weak. In those cases, there are different aspects of weak grid that need to be addressed in different ways. I think I mentioned OEM design processes have improved. No, nothing is bulletproof, but definitely there has been quite a bit of influence of the project experience into those processes. Unfortunately, weak grid systems continue to be complex and require interactions of stakeholders like reliability entities, transmission companies, when there is an issue that needs to be resolved. So those processes takes time and requires data to be exchanged and complex interactions to be understood. That unfortunately is now getting better in the sense that it's more frequent, that this complexity has to be understood. Hopefully the industry continues to understand these problems better so that we can address them sooner collectively. I mentioned grid forming. I don't mean to do this discussion about grid forming, but I did want to mention that grid forming is a great technology that is expected to be quite effective for aspects related to rate of change of frequency or voltage angle jumps behavior, or potentially system restoration. The power transfer constraint systems is not necessarily going to be the main advantage of grid forming. I think advanced grid following inverter-based resources may have comparable performance in that particular regard. Okay, those are the slides that I have. Thanks for paying attention. And I'm happy to discuss any questions that you may have at this time.
Okay, thank you, Sebastian. And I'll remind the people on the line of the Slido, if you have questions, please feel free to enter them. And if we don't get to them all today, then Sebastian will answer them in the next couple of days, and we'll get that out to you afterwards. So I was thinking about the Odessa event, Sebastian, and I think that it's on other people's minds as well. And I see that in the first question here that Russ asked, is slow active power recovery appropriate for voltage control problems? Recent presentation on Odessa disturbance identified this as a problem. I'm sure you've been involved to some extent in the Odessa situation. Could you give a little bit of background on that and kind of ease into this question?
Sure. I wasn't too involved in the Odessa disturbance, so I will refer to the subject in general. So when you, so in inverter-based resources, you would typically, I think everybody in the industry reduces the amount of active power injected during the fault. If you don't do that, you end up tripping equipment. There is a lot of angle shifting in between buses that causes current circulations and equipment end up tripping. So for this reason, for many years, inverter-based resources tend to reduce active power. The most frequent way of doing that is by looking at the voltage magnitude, although there are more sophisticated algorithms in the industry. So during a fault, inverter-based resources will reduce the active power. Now, the question is, once the fault is clear, how do you return from that reduced active power to the pre-fault active power? So in weak systems, if you do that too quickly, usually you will see that the voltage magnitude is negatively affected. The voltage magnitude will tend to collapse like in one of the slides that I show on the right from the field recordings. So slowing down the active power recovery is one of the ways of improving the voltage behavior. Now, that's not the only way. Really, what is needed, what the bulk power system needs is that the reactive power that is required to sustain the increase in power transfer is available at the time before you increase the power. So if you have terminal voltage control at the inverter-based resource and adapt your reactive power to what the grid needs, you may be able to recover power faster. So this is not only about recovering power slowly, it's actually coordinating the availability of reactive power after the clearing with the recovery of active power. Reactive power has to come first to facilitate the conditions to transfer the power out of the inverter-based resource. So I don't know if this answered the question, but at least that's the way I think of this particular subject between voltage control and active power recovery.
There's another aspect to the Odessa problem also, Sebastian, that might be interesting to explore just a little bit, and that is that it seems that the knowledge and information that the OEMs have, which they use in their design and analysis process, and recommendations that they make don't always get picked up and implemented by the project developers who are doing the project. Mm-hmm. Is that something that you're familiar with in your experience, and do you have any suggestions for how to better address that?
I mean, there is a challenge that I think we all collectively have, in that there are more of these system events and conditions that require a particular behavior or require these features improvements. And these features in the inverter-based resources make a difference. Now, if we don't have processes to identify those in the study phase, and then maybe instruct the manufacturers to include those, or the manufacturers have different configurations that are possible, and maybe they don't use the configuration that's specifically useful for the application, this advantages of the inverter-based resources gets lost. So definitely, we are all challenged collectively in making sure that the manufacturer has clear signals on how to configure the inverter-based resources, and then the manufacturer has the bookkeeping mechanisms to, among all the possible configurations of an inverter-based resource, use the one that is appropriate for the application. Not only at the time of commissioning, but during the lifetime of the plant. I don't know if that addresses what you want to discuss, Charlie. See that?
Yeah, I think that that covers it. Let's see. Okay, this one just popped up to the top here. You said GFM and GFL, grid forming and grid following, cannot operate for short circuit ratios below 1 and no load. Does it mean the controller becomes unstable or the line has no capacity for power transfer?
Right. So grid following and grid forming are related to different ways of controlling the active and reactive power from the source. Now, a transmission system has its own limitation. So there is a limit in the amount of power you can transfer through a line or through a long corridor. So it doesn't matter if you have grid following or grid forming, those limitations still exist. So in this case, it wouldn't be necessarily a capacity from thermal capacity limit, but it would be a maximum amount of power you can transfer through the power system, through the let's say long transmission line, for example. There is a limit to that. That's well known, has been understood by the industry for many years. That still applies. It doesn't matter if you have grid forming or grid following. So my comment was that grid forming can operate with short circuit ratio 0, but not in the conditions where you're transferring all the power through a weak connection. So when you have this power transfer challenge, where you're transferring all the power out of the inverter-based resources through a weak system, GFM, the same as GFL, would have a limitation of the transmission system itself. In terms of practice, what may happen is that it could be that some of the control loops get unstable and you see trips in the inverter-based resource. But those things are mostly a manifestation to the fact that there is a limitation of how much power you can push through a system.
Okay, that's very clear. Question on protection. Some IBRs are provided with angle shift protections. Any recommendation on the need or considerations regarding the settings for this protection?
Yeah, so I think the question is correct. So some IBR. So how are we going to define a requirement if some IBR don't have it? So that's one of the challenges first. So in principle, trying to define a setting for a protection of IBRs is complex because different IBRs have different approach and controls. In fact, some IBRs may not have any trip related to a maximum angle excursion, although they may have some other mechanism why they trip. I think in general, my recommendation would be to consider having functional requirements. So if there is an angle shift of this amount, then the inverter-based resource is expected to tolerate it. Now, how the inverter-based resource manufacturer does that, it kind of will depend on their details, how the control is coded and what type of signals they use for protection. So I would tend to discourage, sorry, I don't mean to not answer the question, but I think the idea would not be to define a setting for the protection, but mostly to define what is the functional specification, what is the type of angle shift that IBR is expected not to disconnect in, so to tolerate. That will be more conducive because in that way, independently how the inverter-based resource manufacturer does this, you'll be covering, you can specify a particular behavior.
Okay, good answer, thank you. Here's a question from Ray Walling. SCR is a fundamental frequency metric, but IBR inner loop instability modes tend to hundreds of hertz. How applicable is SCR as a screen for these instabilities?
Yeah, hi Ray, thanks for staying all this time. SCR is a very simple calculation, and we use it as an estimation of problems that are a lot more complex than the calculation, no question. SCR is imperfect. I think SCR has been extremely helpful to identify, at least to differentiate the short circuit ratio 20 from the short circuit ratio 1.5 applications. And the only thing it means is that the short circuit ratio is less than a particular number. We collectively need to pay more attention to the application. It doesn't mean that for sure we're going to have problems or for sure no, we're not going to have problems. In general, SCR is used to make a decision to study a particular application with electromagnetic transient tools, and those will be the tools that will be able to assess the type of problems that you mentioned. So I agree with your comment, but SCR, we shouldn't overstate how much we obtain from an application by calculating the SCR.
Okay, thank you, Sebastian. Question on dynamic performance. Do grid forming inverters have better or worse dynamic performance than that of grid following inverters and stiff grids?
Well, which grid following and what grid forming? So I for sure there in the industry grid following inverters that have worse performance than grid forming inverters, and for sure there are grid forming inverters that have worse performance than grid following. So I think it's great to, and I'm sorry, maybe my discussion also in the conceptual way, I wasn't specific about this. It will depend on the details. I mean, in today's industry, you find grid following technology that can operate in power transfer challenges with short circuit ratios of 1.2, and some that cannot operate with short circuit ratios lower than 5. So there is such a big discrepancy in the different products that are available and even connected in the grid. I think conceptually my point was that for the power transfer problem, there is not conceptually an advantage of grid forming with respect to grid following. For other aspects like Rokov and voltage angle jumps, there is definitely an advantage in grid forming.
Okay, I'm going to jump to this one on DER because we haven't had any DER questions so far. Any comments on a group of IBRs in the distribution system and potential conflicts with weak grid conditions and IBR's active anti-islanding schemes?
Yeah, that's a good point. So the examples that I show are mostly transmission related, but definitely the risk of interactions of different electronic control devices is there in distribution systems as well. Systems tend to be more resistive, and that changes a little bit things, but the risks are there too. With anti-islanding, of course, if you have active anti-islanding, it's basically a destabilizing function, right? So active anti-islanding, you're continually doing a little bit to destabilize the grid to make sure that there is a grid there that keeps the magnitude, the grid quantity stable. If the grid is not there, the system, the magnitudes go unstable, and you use that to detect the islanding conditions. So active anti-islanding could potentially create some challenges in weak grid conditions. Not necessarily. It would depend what concept.
Okay. I'll take this one on interactions. When you discuss interactions with a wind farm IBR, is the interaction with each inverter separately at the wind farm or with the park controller? I think you touched on that.
Yeah. So the subjects I referred to were mostly related to fast controllers that you will find in the converter control. Those are maybe the more difficult ones to identify and to resolve. You can have problems of plant controllers in weak grid. In fact, in some applications where there is one particular contingency that makes the short circuit ratio deteriorate significantly, the plant controller, particularly the voltage regulation of the plant controller, is the one that is more exposed to that change even than the controllers at the converter level. So it could be that you have plant controls that go unstable with grid conditions. The solution for that tends to be relatively simple in the sense that if you tune the control, the plant level control, considering the weakest condition, you will find that the stronger conditions are stable. So to the extent that that is part of the tuning exercise, that works. There is a problem in some areas where there are requirements to have extremely fast response times in voltage regulators. So in plant level voltage regulators. So in those cases, it's challenging. At the time of commissioning, the controllers are tuned very fast, but then you could have a weaker condition, they could go unstable. That's some of the risk of requiring very fast response time in plant level controllers. But those are not the problems I referred to before, but those exist.
Okay, the next two questions are kind of related, Sebastian. As IBR capacity grows to dominate large parts or all of a power system, will higher overcurrent ratings be needed to maintain adequate system fault levels? And related to that, do you recommend writing performance compliance rules with a view that grids will get weaker in the future?
So regarding the higher overcurrent, I think right now, like the industry, I think I'm seeing two forces here, right? So one is on the protective reline side, experts of protective reline have a preference to have an increased current injection or short circuit contribution from inverter based resources. And then on the inverter based resource OEMs or side, there is a push to say, well, if we have to increase the current, the short circuit contribution, we have to increase the rating, and that has a cost. Why don't we review the way we do protection? I honestly, I don't know where that's going to end up. I think both sides are going to have to sort of adapt. There are several places in the world where there are requirements for higher current contribution is being entertained from IBRs. And there is also quite a bit of work in looking at concepts of protection that don't rely on overcurrent, on high currents as much to detect fault conditions. I am not sure where that, where the industry is going to end up with that. I do see an increased interest from protective reline community to understand the contributions to faults of the different products that I work with. And I think I'm hoping that that dialogue will help both sides of this discussion to progress towards something that.
Yeah, I think that's a real interesting question for the future. Okay, I'm going to wrap up with this last question We're right at the top of the hour, Sebastian. I'm not exactly sure what the question is, but it's how to define a group of IBRs that may be interacting with each other and kind of the implications of that. It's an interesting question.
So it's hard to find. So most of the typical planning exercises like low flow, short circuits, and stability simulations would typically not show that you have that problem. And even if you have the plants operating in the field, it is not easy to identify. So the way you identify that is by, let's say, if you have reactive power from one, like the wind turbines I mentioned before and the SVC, and you see that both of them, the reactive power in one source is increasing and the other one is decreasing, you can see that there is an exchange of reactive power in between the two at that particular frequency. Now, to get to the visibility of the quantities to be able to identify that, it requires either EMT studies or very fast recording of data. So it is not easy to identify, it's really complex. Sometimes the more difficult part of solving a problem is to identify it to that level of detail.
Yeah, that's an interesting one. Okay, so I guess we're just over the top of the hour. We're going to need to wrap it up. And Sebastian, thank you for this very informative and educational webinar. I know I learned a lot of new things today. I hope everyone else did as well. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll get the responses to the unanswered questions posted as quickly as possible. We appreciate your engagement and would like to invite you to our next webinar featuring Derek Stenklick of Telos Energy on rethinking resource adequacy. This will be held next Tuesday, November 16th at 4 p.m. Eastern. The next ESIG G-PST webinar will be held at the end of the month on November 30th, featuring Mark O'Malley, ESIG's chief scientist, on the G-PST research agenda. Further information on all of the webinars and workshops can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Sebastian, I want to thank you again for this very timely webinar and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.
Thank you, Charlie.